Hi, in this video we will introduce the notion of orthogonal projection of a vector onto a subspace. This would generalize the projection of a vector on another vector, and that's why I will start the lecture by recalling what was projection of a vector on another one. So if you have two vectors in Rn, then we define this projection of vector v onto vector u. Well, geometrically that was, so this is u, this is v. What we meant was the shadow, the orthogonal shadow of v in the direction of u. So this is what we call projection of v onto u. And well, the definition was u dot v over u dot u. This is a scalar, then scalar multiplied to vector u. Now we want to replace this vector by a subspace. And what geometrically we mean is that, well, if you have, let's say, a two-dimensional subspace and a vector like v, the projection here means that, again, find the shadow of that vector v onto the subspace. Well, let's see how we do that definition. So we need to fix a subspace. So let W be a subspace of Rn. And to be able to define projection of V onto subspace, we have to fix a basis, not a regular basis, an orthogonal basis. Let W be a subspace and U1, U2 up to UK be an orthogonal basis for W. Okay, so we fix a basis, orthogonal basis. You can fix any orthogonal basis you like, but then for any vector v in Rn, we define the orthogonal projection of v onto W to be, well, the notation is, as I mentioned above, projection of v onto the subspace W. This is going to be, well, take U1, dot product U1 with v, and then this guy. Oops, why is that? Okay. Then this is a scalar, multiply that scalar multiplied by U1. Then U2 dot V over U2 dot U2, this is scalar multiplied by U2, and this goes up to UK dot V over UK dot UK. What you need to note here is that this is basically projection of V onto U1, then added to projection of V onto U2, and go up to projection, oh, I forgot to put UK there, but that would be projection of V onto UK. Well, also we define something else, moreover, the component of V orthogonal to W is defined, well, we have a notation for that. This is projection, not projection, sorry, perp of V over W. Compared to projection of V over W, we've defined perp of V over W. This is going to be V minus just projection of V onto W. Well, we will study the properties of these guys and why these guys are important. But here, in the rest of this video, we will do some examples of computation of these components. Okay, so V is given and W is a span of two vectors. First thing to note is that W is given, you have to find an orthogonal basis. Well, we don't have the whole tool to do that, but in this case, the given vectors are orthogonal, so they will form an orthogonal basis. So 1, 1, negative 1. Let's call this one U1. And U2, which is 2, 3, negative 2, 1, are orthogonal, and since they are spanning the W, is an orthogonal basis for W. So that means that we have everything. Now we can start computing projection of V over W, which is nothing but sum of projection of U over U1, V over U1, and projection of V over U2. Well, what are these? We know that dot product V U1, so 1 times 0 plus 1 times 1 plus negative 1 times 0 over 1 squared plus 1 squared plus negative 1 squared. Dot U1 plus U2 3 U2 dot V 3 dot times 0 plus negative 2 times 1 plus 1 times 0 over 3 squared negative 2 squared plus 0. Oh, plus, well, not 0. I have 1 squared there. Dot U2, 3, negative 2, 1. So we have to do these simplifications or computations there. Okay, here is 1 over 3 multiplied to U1. And over there is negative 2 over 14. Well, that means that we have negative 1 over 7 multiplied to U2. And that gives us what? This is 1/3 minus 3 over 7. Here's 1/3 plus 2 over 7. And this is negative 1 over 3 minus 1 over 7. Okay. Here, this is 7 minus 9, which is negative 2 over 21. That's 7 plus 6 is 13 over 21. And this is negative 7 minus 3 is negative 10 over 21. That is the projection. So projection of V over W we found. Now perp of V over W, this is just V itself minus the projection, which is what we found. Yes, just found it. And this needs just one simple step. 2 over 21. 21 minus 3 is 8 over 21. And this is just 10 over 20. So we computed both components that we were looking for. But this other one, okay, W is a line, well, line through the origin. That means it is a subspace. And it has a direction vector 2, 1, 0, negative 2. This right away, you see, that means that all the vectors which are parallel to this vector, and that vector itself is going to form a basis. So let me call this U1. Oops, this is bad. Okay, now U1, and this is an orthogonal basis for W. And in that case, projection of V onto W is nothing but projection of a V onto U1, which is, well, dot product of these guys, 2 times 1 plus 1 times 3 plus 0 times 2 plus negative 2 times 1 over 2 squared plus 1 squared plus 0 squared plus negative 2 squared times scalar multiplied to U1. Here, this cancels that one. This is just 0. That's 3 over 9. So it will be 1/3 of 2, 1, 0, negative 2. And that is 2 over 3, 1 over 3, 0, negative 2 over 3. Now that we have projection, finding perp of V orthogonal to W is not difficult. Just V itself minus projection of V onto W. So 2/3, 1/3, 0, negative 2/3. This is 1 minus 2/3 is negative 1 over 3. 3 minus 1 over 3 is 9 minus 1. This is 8 over 3. This is just 2, and that is 5 over 3. So we computed both components of V with respect to W. In the next videos, we will study the properties, and we will introduce something very important: orthogonal decomposition of a vector with respect to subspace.